Even nonsense can be meaningful. Mathematics is more than just things free of inconsistency. It's more than just that which is the case. Sometimes we're confronted with things that are really nonsensical, or just things that are flat out wrong. And when we're confronted with things like that, we should really have a feeling or a need to salvage the situation. We should take the nonsensical or the wrong thing and try to salvage it. Try to think of some sense in which it might make sense.
So what's the sum, n goes from 0 to infinity, of 9 times 10 to the nth power?
The party pooper simply says the series diverges.
And the party pooper is right. This series diverges. And why does it diverge? Well, it's a geometric series with r equals 10, and that common ratio is bigger than 1.
But let's try to salvage the nonsense.
Well, remember back how we looked at the sum, n goes from 1 to infinity, of 9 times 10 to the negative nth power? And this was equal to 1, but we could also write it as 0.9999, where the 9s keep on going that way. Well, in this situation, I'm contemplating something sort of the opposite. I'm thinking of the sum, n goes from 0 to infinity, of 9 times 10 to the n. Well, what is that? When I plug in n equals 0, I get 9 times 1, which is 9. When I plug in n equals 1, I get 9 times 10, which is 90. When I plug in n equals 2, I get 9 times 100, which is 900. And I'd keep on going. So one way to write this might be, well, that first 9 plus 90, that's 99. 99 plus 900, that's 999. It's as if I could write it with 9s going this way.
And what if we add 1 to that?
Well, I mean, it's not really a number, right? But I can still write it down. So I'll write down a number that's just 9s going this way, and then I'm going to add 1 to that number. What do I get? Well, 9 plus 1 is 10, carry the 1. 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 9 plus 1 is 10, carry the... And I'm going to keep on doing that, right? So it looks like this thing, which is 9s all the way that way, plus 1, is 0.
So whatever this thing is, it's a thing that if I add 1 to it, I get 0.
So what is 999 with dots all that way? It's sort of equal to negative 1. Because negative 1 is a thing that I can add 1 to get 0, and when I added 1 to this thing, I got 0.
Sort of makes sense.
So if I just ignore convergence altogether, what would it tell me to do? I'm trying to evaluate the sum, n goes from 0 to infinity, of 9 times 10 to the n. Well, that would be 9 times the sum, n goes from 0 to infinity, of 10 to the n. It's a divergent geometric series, but let's just pretend the formula still worked. How would I calculate the value of that series? That'd be 9 times, and the formula for this is 1 over 1 minus the common ratio, which is 10. Of course, that formula is only valid if it were a convergent series, and it's not. But let's just pretend. What is this? This is 9 times 1 over 1 minus 10. That's 9 times 1 over minus 9. Well, 9 times 1 over minus 9 is minus 1. Which is sort of what we're seeing here, right? I mean, if you're just ignoring convergence, it looks like it's telling us that the value of this series, I mean, it doesn't have a value because it diverges, but the value of this series maybe should be minus 1. And that's wrong because the series diverges. But that's maybe the best of the wrong answers. Well, we can keep going with this. For example, let's do some more calculations. So let's start with this weird number, which is 9s all that way. It's not really a number, but there we go. And let's multiply this by 5. What do we get? 5 times 9 is 45. So I'll put the 5 down there and carry the 4. 5 times 9 is 45, plus 4 is 49. I've got 4 to carry. 5 times 9 is 45, plus 4 is 49. got a 9 there, and I got to carry the 4. 5 times 9 is 45, plus 4 is 49. Well, you get the idea. I'm going to keep on getting 9s that way. So 9 times 5 is 5, 9. Well, what is this? Well, what happens if I add 5 to it? 5 plus 5 is 0. Well, it's 10, but I got to carry the 1. 9 plus 1 is 10, so I put it down to 0 and I carry the 1. 9 plus 1 is 10, so I put it down to 0, carry the 1. Right, so 5 with a bunch of 9s here plus 5 is 0. So maybe then this number looks to be a lot like negative 5, because negative 5 is a thing I can add to 5 to get 0. And we already saw that 9s this way looked a lot like negative 1. So it seems like I've taken a number that's playing a role sort of like negative 1, and I've multiplied it by 5, and I've got a number that's playing the role of negative 5, which I could tell because when I added 5 to it, I got back to 0.
And that worked better than it should have. What if we took 9999999 and multiplied it by itself?
So I've got 9s all the way to the left times itself. 9s all the way to the left. And what is that product? Well, 9 times 9 is 81, so put the 1 down there and the 8 up there for the carry. 9 times 9 is 81 plus 8, which is 89, so put the 9 there, and I got to carry this 8 now. 9 times 9 is 81 plus 8 is 89, so I'll write the 9 down there, and then I got to carry the 8. And I'm going to keep on carrying 8s along the top, and I'm going to keep on writing 9s along the bottom. So it looks like working on the first digit here, 9s all the way to the left times 9 is just 1 with 9s all the way to the left. But that's just working on this first digit. Now I've got to move to the next digit on the bottom. So I'll put a 0 there, and it'll be 9 times 9 is 81. So I put the 8 up there and the 1 down there. 9 times 9 plus 8 is 89. So I put the 9 down there and then the 8 up there. 9 times 9 is 81 plus 8, which is 89. So I'll put the 9 down there and I'll put the 8 up there. And I'll keep on going the same exact way, right? So working on that second digit, I've got a 0, a 1, and then all 9s. Then I got to work on the third digit on the bottom. I'll put down 2 zeros here, and then it's exactly the same pattern. It's going to be 1 followed by 9s going on forever. And then to work on the next digit on the bottom, it'll be 3 zeros, and then the same pattern of 1 followed by a bunch of 9s. And it's going to keep on going like that. Well, after I do all the digits along the bottom in this algorithm, I'm supposed to add them all up. So now I've got 1. 9 plus 1 is 10, so I put the 0 there and I carry the 1. 1 plus 9 plus 9 plus 1 is 20, so that's 0 here, and I got to carry a 2 there. 2 plus 9 plus 9 plus 9 plus 1, well, that's 30. So I'll put the 0 there, and I'll put a 3 here. And I'm going to keep on going like that, and I'm going to get zeros all the way across here. So what just happened? Well, it looks like we started with a number that's playing the role of -1, and we multiplied it by a number that's playing the role of -1. And when I actually did that multiplication, the answer that I ended up getting looks to be 1, which is just what I'd hope it would be. So it really is seeming like it's working. I mean, we started out with this nonsensical thing, right? This divergent series. But by sort of taking the nonsense seriously, we've ended up getting a system that works sort of like the negative numbers. And in fact, computers do store negative numbers this way. Of course, computers usually don't work base 10, they usually work base 2. And when you work base 2 and do the same kind of game, you call it 2's complement arithmetic. And this sort of thing comes up in just pure mathematics. This sort of thing is often called the p-adic numbers, and in particular, when we're using powers of 10, 10-adic numbers. So mathematics is so powerful that even nonsense can lead to a reasonable theory. It's one thing to win battles just by force alone, right? To be great by virtue of simply being correct all of the time. But it's something else entirely to win those battles when you're weak. To be on the right track even when you're entirely wrong. And I think the fact that mathematics works like this really shows that there's something to it. It's not just symbols that we're pushing around on a page. We're really out there exploring something that's really there and something really beautiful. And we're just fortunate to be able to get to take part.